When developers interact with a database, they rely on a simple API, get and put. This interface hides the hostile environment inherent to distributed software. A key value store is a non-relational database where a unique string maps to an opaque blob of data. These systems manage session states, user shopping carts, and global configurations. The most basic architecture is a single server running an in-memory hash table. Storing everything in RAM makes read and write operations extremely fast, allowing the server to answer queries with minimal latency. However, vertical scaling, adding more CPU and memory to one machine, reaches a hard physical limit. Eventually, the hardware cannot accommodate more RAM, and the hash table can no longer grow. Once that memory limit is reached, the single server model becomes the primary bottleneck. To serve millions of users and withstand hardware failure, the system must move beyond a single machine and toward a distributed architecture. Initial strategies to delay hardware limits include data compression and evicting cold data to disk, while keeping only the most active keys in memory. Even with these optimizations, a single server eventually reaches capacity. Managing massive datasets requires a transition to a distributed model. This requires moving from a local hash table to a distributed hash table, where data is split and stored across a cluster of independent machines. This setup must support high traffic volumes and maintain availability even when individual components fail. While distributing data solves the capacity problem, it introduces the challenge of keeping that data organized and synchronized over an unreliable network. In network engineering, communication breaks between nodes are an operational reality. Cables get cut and routers fail, causing network partitions. The CAP theorem defines 3 properties for distributed systems: consistency, availability, and partition tolerance. Because network partitions occur in any real-world cluster, partition tolerance is a requirement. This makes a system that provides both perfect consistency and 100% availability impossible over a network. In a CP system, data is kept perfectly consistent. To ensure every node has the same data during a network outage, the system will block new reads and writes until all nodes are back in sync. An AP system prioritizes availability. It will return a response to the client immediately, even if it means serving data that is out of date or incorrect due to a network split. Banking systems often choose CP to prevent account errors, while shopping carts might choose AP, so a user can always add items to their bag, even if the count is temporarily inaccurate. Most massive consumer platforms choose AP for its speed, opting for eventual consistency. This means the system accepts data conflicts and resolves them after the fact. The first mechanical problem is how to distribute the data evenly across a fleet of servers. Using basic modulo math to map keys to servers works until a new machine is added. Changing the number of servers causes the mapping to shift, forcing nearly all data to move and saturating the network. To manage this, we use consistent hashing. In this model, servers are mapped to positions on a circular hash ring. When a key is dropped onto the ring, the system walks clockwise. The data is stored on the first server it encounters. This ensures that when a node is added or removed, only the data belonging to the immediate neighbors needs to be remapped. However, a basic ring often results in servers clustering unevenly. This creates hotspots where a few nodes take on significantly more load than others. We resolve this using virtual nodes. Each physical machine is represented by multiple points on the ring. This allows for heterogeneity. A server with more CPU and RAM can be assigned more virtual nodes to handle a larger share of the traffic. Consistent hashing solves data distribution, but storing data on only one physical node leaves the system vulnerable to a single point of failure. To achieve high availability, data must be asynchronously copied to n distinct servers to ensure it survives hardware failure. The system walks clockwise from the key's position and places copies on the first n unique physical servers it finds. Because these copies are made asynchronously, individual replicas will fall out of sync with each other during active writes. Quorum consensus provides the mathematical framework for synchronizing these nodes. A coordinator acts as a proxy, managing requests and acknowledgements. Here, n is total replicas, w is the number of write acknowledgements required for success, and r is the number of required read acknowledgements. For maximum speed, we set w or r to 1. The coordinator returns our instance as soon as the fastest server acknowledges the operation. For strong consistency, we ensure w plus r is greater than n. This ensures at least one responding node has the most recent update. This quorum model allows us to tune the exact trade-off between latency and consistency, though optimizing for speed ensures that conflicting versions of data will eventually enter the cluster. In systems optimized for availability, concurrent writes during a network partition result in diverging datasets across replicas. If two clients update the same key while servers are isolated from one another, the database ends up with two different realities. We track these versions using vector clocks. This metadata records the server and a version counter for every update. When a client later requests this key, the database identifies conflicting vector clocks and returns all versions of the data. Under eventual consistency, the system requires the client application to merge the data and write back a reconciled version. Because vector clocks can grow quite large, many systems use a last write wins strategy based on timestamps, accepting some data loss in exchange for lower overhead. Providing sub-millisecond availability at scale requires shifting the burden of data reconciliation from the database to the application layer. Scaling a key value store is a transition from the memory limits of a single machine to a complex global cluster. The engineering cycle involves partitioning data across a hash ring, replicating it for redundancy, and defining the quorum logic that governs node synchronization. The simple put and get interface is a facade that hides the trade-offs required to keep data accessible over an unreliable network. Operating this architecture at scale also involves hinted handoffs, gossip protocols, and Merkle trees to maintain integrity when hardware fails or data centers lose power. Senior system design involves mathematically defining the specific failure modes a cluster is built to tolerate.